Hello everybody and welcome to our video today where we are talking about physics chapter 8, light and optics. So the first thing we're going to start off with are these four images right here. I'm going to move the camera so you can see because I really recommend you recognizing those four blue images, okay? And I'll explain them in just a moment, but I would recommend taking a picture of them right now while we're close up. And I will explain them as we go, but those are just some important images that you should definitely be able to recognize, okay? So first we have concave, make sure you can see. So we have a concave mirror, okay, and would reflect light like this. Then we have a convex mirror, vex, like that. This one's kind of like a cave. This one, no, convex mirror. If you were to take like the back of the spoon, for example, would reflect light that way. Then we have convex lenses, which also converge. Okay, so the convex lenses, you should recognize that, and converge. And then we have a concave lens, which actually diverge, and you can see that as the light is going apart, right? So those are diverging. So those are just some important images that you should definitely recognize. I'm just trying to make sure you guys can see it. So next we have our little trick up here, and this is just for your memory. UV equals IR. This means upright is virtual, inverted is real. And when we're saying virtual or real, we're talking about the images. So we have a real image as when the lines intersect. That means you have an inverted image, okay? And that means it also has a negative magnification. Now, if we had a virtual image, the virtual would be upright, right? So the lines do not intersect. This gives you an upright image and a positive magnification. We can see that down here. There we go. So you can see that down here in these examples, okay? So here we have our concave mirror. You see that, as well as our convex lens, you see these lines crossing, right? You can see these lines crossing. Then you have the convex mirror and the concave lens, and those lines only cross if you trace them back, okay? That's the only way you can get these lines to cross. But initially, right, they do not cross, which means the image would be upright and it is a virtual image, okay? Next, we're going to be looking at the sign, the distance image, okay? And that's going to represent our DI in this equation that we'll get to, but we need to look at the sign of the image, okay? So basically the distance. So for mirrors, it is positive, it has a positive image distance if the object and the image are on the same side. So if we're looking at the mirror, right, the crossing, right, is where we will see this image. And we would know that the light is coming from here and going through the mirror this way, or supposedly. And that means that in this case, if our object was here, we would have our object and our image on the same side, which means this would have a positive distance image value, okay? And for the convex lens, now we're looking at lenses. So let's take a look at the lens, for example. For the lenses, it would be a positive image distance if it's opposite, if the image is on the opposite side of the lens as the object. And we say where the light is going, so you know where that image is actually going to be, right? So if we have opposite side of the lens as the object, if let's say for our lens, let's say if we were looking at this lens right here, right, the convex lens, if we have our object on this side of the lens, right, you're looking through glasses, for example, and the image would also be on this side because this is where the lines are crossing, right? So that would actually be a negative distance image because the object that you're looking at as well as the image is on the same side, okay? So they're both on this side of the lens. And then so that's just two examples. But for mirrors, if the object and the image are on opposite sides, okay, for example, in this convex mirror, right, if we had our object on this side, right? Light is coming here. The image created would actually be back here, right? And that means that the object and the image are on opposite sides of the mirror, which means that that would have a negative distance image, or image distance, sorry. And then finally, for the positive distance image when we're looking at a lens, is when we have the image and the object on opposite sides. Okay, so we can see that in this concave lens, right? If we're looking and light is going in this direction, the image would be back here because you're having to trace these lines back. So the image would be back here. But if you're looking at, you know, an object through some glasses, for example, you would have the image being created on the opposite side of the actual object, which would mean that this is a positive distance image for this lens. So I know that was a lot, but looking at these examples, hopefully that made more sense. Another important thing to look at when we're looking at these examples is the focal length. So concave mirrors and convex lenses have a positive focal length because they converge. And you can see that, right? So those converge. And then we have the convex mirror and the concave lens that have a negative focal point because they diverge. Okay, so just think diverge, you know, if you're thinking of some two people fighting, for example, if they're diverging, you know, they're not agreeing, they're going on opposite sides, that means that they are diverging, they have a negative focal length. But if we are looking at, you know, two people who are agreeing and coming together, we would see a positive focal length and they are converging. Okay, so that's just how I remember it. But again, I know that is a lot, so make sure you understand these examples down here. Also, in this section, we're looking at magnitude. So magnitude is just a simple equation. It's negative di, which is distance image, over do, which is the object distance, okay? So magnitude equals negative di over do. And we have this equation right here in the orange box. And we have 1 over the focal length equals 1 over the distance image plus 1 over the object distance, okay? Which kind of translates to the F, right? The focal length equals do times di over do plus di, okay? So that's just another equation that you should definitely know in just being able to manipulate that into a lot of different questions, okay? So finally, we have, we still have a few more things to get to. But we're looking at myopia and hyperopia, okay? So myopia is when the focal length is too short. So if this is the eye, for example, and the focal length produces the image in front of the retina. So the focal point here is too short. Therefore, you would use a concave lens so that when the light is coming in, this focal point is actually pushed back onto the retina, which allows you to see. So this is why people wear glasses. Then we also have hyperopia, which is when the focal length is too far, right? And it's too far past your retina, so you can't really see, which is why you would use the convex lens, which would bring that focal point and put it on to your retina. So those are the two different, ways that people use glasses for their vision problems. Now over here, just some really simple stuff to go through really quickly before we finish this chapter. So we have reflection, which is when the incidence angle is equal to the angle of reflection. So theta 1 equals theta 2, so those representing the angles. Okay, so we see that here. Right, so the angle of incidence equals the angle of reflection. That is reflection. Then we have refraction, and the refraction actually bends light. So it is the bend of light. So N, which is the, here we see medium 1, medium 2. So N equals C over V. And C is the speed of light. And V would be the speed of light in that medium. So we would have, for example, there's a difference of these angles from going between one medium to another. So that's just refraction, the concept of refraction. And we have Snell's law. I just want to make sure you can see this. Then we have Snell's law. I'll bring it a little closer. Oops, sorry about that. looked a little small to me. Then we have Snell's law, which is n1 sine theta 1 equals n2 sine theta 2. Okay, and that is just used for refraction. So you can input some values there and manipulate this equation to determine, an angle or an n value. Then we have diffraction, which is the spreading out of waves when the light encounters an obstacle. So it shows that light is not a stream of particles. If light was a stream of particles, it would go through and it would just automatically come out as one straight line, right? But we see this, if we shine light through one hole, right, it will light up the whole space, which is showing diffraction, just showing the spreading out of those waves. And that proves again that light is not a stream of particles. Then we have dispersion, which the effect allows the prism to split white light. And this just shows the increased frequency of light and an increased refraction index. So that's how you kind of see like the rainbow colors if you're looking at like a crystal, for example, and it really splits into all those rainbow colors. That is dispersion. And finally, the last thing to note for this chapter is the visible light on the spectrum is from 400 nm to 700 nm, and the order is Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Red being the shorter wavelength and violet having the higher wavelength. Okay, so that is everything for this chapter. I know that was a lot of information, but hopefully it helped. Like I said, definitely study those images that we talked about at the beginning, know this equation, and just look at these examples and kind of go through for each aspect that we spoke about, just so you have a good idea of, recognizing all of these aspects of light and optics. So if you have any questions, please put them below. But if not, we'll see you in the next video.